Okay, hi everyone. Thank you so much for joining me on this Monday. Today I think we're gonna kind of transition a little bit and do something pretty cool. We're definitely gonna talk about some different kind of shapes, so hopefully that'll be interesting. But before we get into that, I just want to start off with our icebreaker, which for today is what is your favorite holiday? I was thinking about doing like a daylight savings one because we just had daylight savings yesterday. But I think like we could all agree that daylight savings sucks, so that was gonna be like a boring icebreaker. But because we're like entering that holiday season, like we just got out of Halloween, we're entering Thanksgiving and Christmas and all those um holidays. I just wanted to ask, like, what is your guys' favorite holiday to celebrate? Um, it could be anything, really any holiday. Or maybe like even your favorite national day, like National Donut Day or something. Yeah, let's take a look at what you guys said. Sai says summer break. I actually have no idea if summer break is technically a holiday, but you know what? We'll put it down. We'll put summer break. Oshert says Holi and Diwali, which are both, actually, I should probably capitalize those. Those are both Indian festivals or Indian holidays. Let's see. Minit says Christmas. Yeah, because you get to have gifts and celebrate with family and friends. That's such a good reason. And Vika says National Ice Cream Day. Oh, National Ice Cream for Breakfast Day. Oh, that's okay. Yeah, there's like a national day for everything. I think like every day is a national day for something. Wait, I don't know how to like National Ice Cream for Breakfast Day. That's a big one. Amari says Christmas, and oh, that's so awesome. Okay, another vote for Christmas. Malden says 7-Eleven because we get a discount for drinks at 7. Oh, I didn't even know that that was a thing. Okay, so this is like July. Okay, so free drinks or discount drinks. Okay, I didn't even know that was a thing. Oh my gosh, I just realized I like keep missing the opportunity to ask you guys about like your Halloween costume. So if your favorite holiday is Halloween, go ahead and like put in what your costume is as well. That would be really good. I just keep forgetting that Halloween was a thing. Oshrit says National Bathtub Day. Oh, that's your birthday. Okay, cool. That's cool. What do you do on National Bath Club? National, gosh, Bathtub Day. What does one even do? Bathtub Day. Okay, that was like kind of bad writing. Oh, tax day. Yeah, I don't think that's anyone's favorite holiday. Let's see. Minute says Three Musketeers with two of my other friends. Oh, that's so awesome. That is so cute. Oh, Luffy. Oh, what is Luffy? Hold on. Is this like, am I supposed to know what this is? Okay, they're from manga. Okay, okay, cool. So I'm not a manga person. That's why I don't know who that is. Cool. Okay, cool, cool, cool. So, well, that's really cool. That's really cool. Okay, awesome. And I guess like while we're just talking about random things, because I know we started on like a holiday and then we started talking about Halloween. If any of you guys went to the math league this weekend, how did you guys do? I'm just really curious. I think I was there at the Hawk Creek one. I talked a little bit, kind of like at the end after the team round. I saw some of you guys there, so that was like super cool. But yeah, if you guys went, how was it? How'd you do? And did you have fun? Yeah. Let's see. He says, I was at Vex. Oh, that's so cool. That's still super duper cool. Kevin says it was good and that he had fun. Awesome. Good to hear. Okay, that's cool. I feel like we talked about a lot of random things today. I feel like there wasn't really like one icebreaker. But yeah, if you guys ever want to shoot me an email about like how you did at Math League or any pictures that you want to share, that'd be super duper cool. But no pressure. Just something to keep in mind. Okay, cool. Let's go ahead and jump into some math for today. So, for today, we will be talking about circles. Yeah, so we'll be talking about circle theorems. Circle theorems. I think we need to start off with some de definitions because, like, we all know what a circle is. Um, Hopefully, we all know what a circle is, but I think that we got to do some like formal ways of defining this. So, to start off, can someone give me like the definition of a circle? Like, what is a circle? This might sound really, really basic. It's not a trick question. I'm just curious. Like, what do you guys think? Like a circle. Like, what is a circle? A circle is a circle. It's on the board. Yeah, it's a shape. That's true. It is a shape. Okay, so let's draw some shapes. Here's a shape. Is that a circle? It's round. Okay. I could say like this is pretty round if you ask me. It doesn't have any sharp edges. Is that a circle? Hmm. It's like it's like you guys know what a circle is. Like you can picture a circle in your head, but I want to get to like what is the math like what is the definition of a circle? Like what does it mean to be a circle? Because we say like someone said a circle is round. I mean, this shape is pretty round if you ask me, but that's obviously not a circle. Um Let's see. I think I see some answers from, oh, Oshrit says a set of points that is the same distance from the center. Okay, I think this is like the definition that I'm looking for. I think this is a really good definition, Oshrit. So thank you for putting that in there. Anvika says a shape with a curved line where each point is equidistant from the center. Yeah, okay, I like that too. I like that too. Malden says a shape with infinite symmetry. Oh, that's a very interesting definition. Let me think. I think I want to say like maybe this is correct. I'm a little hesitant, but I think it's like you're kind of like thinking on the right track. I think it's a very unique definition. That's one I haven't heard before. That's really cool, Malden. Um, let's see. Monvit says a circle is the set of all points in a plane that are equidistant from the point called the center of the circle. Yeah, yeah, yeah. Okay, cool, cool, cool. I think yeah, so many. I haven't drawn anything on my screen yet. So I'm trying to like guess. Like what do you guys think a circle is? And then we'll kind of go ahead and draw and talk about it. But yeah. So there's nothing on my screen except for circle theorems. Sai says a perfectly round object that has no corners and all the sides have the same distance from the center. Yeah. So the perfectly round stuff and the no corners, those are like qualifiers of a circle, but they're not necessarily like what makes the circle a circle. So what makes a circle is the fact that you have a point, so you have some point, and we'll call this like your center point. And around the center point, wait, I wonder if can I like, oh, yes, I have shapes. Okay, lovely. So around the center point, you kind of have like, oh, that's like not how I wanted to do this. Go away, go away. Okay, around the center point, you have a circle. Hold on. Okay. Oh my goodness. Wait, I'm trying to draw the circle. Okay, and now I'm going to move said circle so that it's actually centered. Okay, perfect. And then we'll adjust the center. Okay, yay, this is our circle. So I said a circle. Yeah, I tried to use the drawing tool, but I did something wrong. Okay, anyways. Cool. So this is our circle. This is the center point, and what makes a circle is that we have the center point, and every point on this circle is the same distance from the center point. So what exactly is that distance? So what I'm talking about in particular, what is this distance here? What do we call this distance? Oh, do you guys not see anything? Oh, hold on. I should say that I am screen sharing. Okay, no circle. Okay, let's see. Let me try again. This is very interesting. Okay, can you guys see this? Yes. Okay, perfect. Okay, cool, cool, cool. I don't know what happened. That was really weird. Okay, Cool. Cool. Okay. So we have the circle and we have the center point in green, and every point on the circle in black is going to be the same distance away from our center point. So what do we call this distance? I've kind of like drawn it in red. What is that distance? Yeah, it's the radius. Okay, perfect. Thanks, you guys. So this is the radius, and we'll say it's like R. So this is the radius R. So let's say like we're connecting R all the way across the circle. Typically when we're working with circles, we don't really like to have segments like stop in the middle of the circle. If we're ever dealing with a segment, we want it to go on like we want it to touch both sides of the circle. So obviously like I'm starting from the center again, and well, I guess it might make more sense if like maybe I do this in a different color. Um, I'll do it in purple. So like obviously I'm like at the center again and I'm going to a different point on the circle, but because I'm starting like at the center and I'm still going to a point on the circle, like this purple line is still also the radius. But what's interesting is now I'm connecting 2 points on like opposite sides of the circle kind of, and they both go through the center. And because it goes through the center, we call this entire thing the radius. Or sorry, the diameter. That was so anticlimactic. Oh, what the heck? Okay. Oh my goodness. What is happening? Okay, here we go. And this is our diameter. So as you guys can see, the diameter is obviously 2 times of the radius. I think this is all review. Like I think you guys already know all this stuff. But I just want to make sure. Is it clear like what exactly a circle is? Because I think that could be like pretty important sometimes as a definition. Okay, let's see. Okay, cool, cool, cool. Yeah. Oh, Anvika says diameter is a chord that passes through the center. Yeah, very interesting. So we haven't defined a chord yet, so we'll kind of like talk about that later. But I like that you mentioned that. Okay, awesome. Um, Covenant asks, isn't diameter 2 times r? Yeah, yeah, yeah. So the diameter is 2 times the radius. That's kind of what we illustrated here. Yeah, cool. Okay, amazing. Yeah. Cool. So because this is definitions, there's not really like a good example problem. We'll get into like the more complex stuff. And when we do that, there will definitely be lots of examples. So kind of like saying that, let's go ahead and start talking about a couple more definitions because there's definitely a lot of terms to know with circles. And then we'll kind of get into like some theorems. So we've talked about what a radius and a diameter is. And then Vika brought up this idea of like what a chord is. So let's go ahead and talk about. Oh, actually, just kidding. Before we talk about that, Minnie, I saw you had a hand raised. Did you want to ask a question? No. Okay. Okay. No worries. No worries. Okay. So what is a chord? A chord, and I guess I'll draw it on the same circle. This is like our model circle of the day. Okay. So a chord is basically any segment whose endpoints are on the circle. So like this is our chord, because both of the endpoints are on the circle. A chord is something on a guitar. Yeah, so a chord can also be like a musical thing. It can also be like a tie kind of thing. They're all like kind of related in their own way. In a circle, it's a segment that connects 2 different points on the circle. So that's why like the diameter. Remember, the diameter connects 2 points that are like exactly opposite on the circle, and the line passes through the center. So that's what makes it the diameter, the fact that the connection between 2 points on the circle passes through the center. So basically, the diameter, another way of talking about the diameter is that it's a chord that goes through the center. Okay, so this is pretty cool. Let's see. Can a chord be the diameter? Yes, yes, yes. Um, Are chords like a vertex just for circles? So I would say chords are more like diagonals. Because remember, if you think about a diagonal and like a polygon, like a square or a pentagon, they connect up like vertices that that are not adjacent. In the same way, a chord connects two vertices or 2 points on the circle. So I would say a chord is more like a diagonal. Let's see. Come and ask, can there be more than one chord? Yeah, absolutely. Just like circles can have, or just like polygons can have more than one diagonal, chords can have, or circles can have more than one chord. Okay, sorry, that was like, kind of confusing. Um, a chord can absolutely be in the middle. It's just when it's in the middle, we call it the diameter instead. Okay, awesome. I think we are all doing well. Cool. So then, now that we have a chord, we also have another thing called a secant. And in retrospect, I think I should have made my diagram a little bigger, but that's okay. No big deal. I'm trying to think of another color. What color have I not used yet? I guess I haven't used green like precisely on here, so you will use green again. Okay, so we have a chord. We also have something called a secant. So a secant is like pretty interesting. It's very similar to a chord, but what makes it different is, hold on. Let me just write secant. Okay, what makes it interesting is that it's a line. So remember, a chord is a segment, but a secant is a line. So we say that a secant intersects the circle at 2 points. You could say like a chord is like a part of a secant because the chord is just a segment. It stops and ends on the circle. The secant and like goes beyond the circle, so it kind of goes throughout the entire thing. So this is like what a secant looks like. They're very similar, but remember a secant is a line and a chord is a segment. So a chord stops and ends on the circle. A secant goes on and on. It just intersects the circle. Um, okay, is that clear? Like, is it clear what the difference between these is? So Ashra asked the amazing question of what's a tangent? And we are about to get to that. Before we do, I just want to make sure any questions here on like what a secant is. Okay, no, I think we're good. Okay, so you guys are eager to find out what is a tangent? A tangent is basically a secant that intersects the circle in exactly one place. So let's go ahead and draw what that tangent looks like. If I can find a good color. We will use this teal. Okay. There we go. Okay. And this is our tangent. So notice how the tangent only touches the circle exactly at this one point. But if we look at a secant intersects the circle at 2 points. And actually, a chord does the same thing. A chord intersects a circle at 2 points as well. But the tangent only touches the circle at one point. It's still a line, so it kind of like goes on forever and ever, but it only meets the circle at one point. So that's what makes a tangent super duper special. Because typically, like any other line that you draw will intersect the circle in exactly 2 places, but a tangent only does it in one place. So it's a very unique thing, and we find a lot of really cool properties with tangents. Um, okay, cool. Let's see. Um, Monique says a chord is a line segment and a secant is a line. Yes, thank you so much, Monique, for summarizing that. Well then, yes, we will absolutely get to some problems. I just want to make sure we have all these definitions down because otherwise the problems will be a little more complex. So yeah, we'll get to some. Um, Oh, so some of you guys are asking, is this like tan and sine? Okay, so like trigonometric functions. And I think Anvika has answered this. They are related in some way. So the trigonometric stuff like tangent, secant is actually a function and sine. These are all like I would say they're semi-related to the circle stuff, but they're more related to like triangles, I would say. So trigonometry is like related to triangles, but there is definitely like a relationship between triangles and circles. That's definitely a little bit more complex than what we can get into today, unfortunately. But yeah, they're definitely related. that's why their names are the same. Especially like the secant stuff. But we cannot get into that today, sadly. Maybe you'll encounter it one day. Okay. Cool, cool, cool. His heart says so. Chord is a line sibling and the secant is a line. Yes, that's correct. Malin says, isn't sine SI? Yeah, so sine is actually spelled with an E. Like if you spell the actual function, it's like this. We just like abbreviate like this. Same reason, tan is actually tangent. Yeah, just like a little fun fact, I guess. Okay, I'll go ahead and erase that because it's not relevant. Okay. Um, Oh, Asher says sine H. Yeah, so this is like a version of the sine function, but it's like hyperbolic. So it's like super crazy. Do not worry about that. You literally don't even encounter that in high school. Like, I don't think I dealt with that one time in calculus. So like you'll be fine. Like, don't worry about this. Um, okay. Yeah. Cool. I see a lot of interest in trigonometry. This may be like a potential future lesson, but to be realistic with you, like you don't really use trigonometry very much in high school. Like maybe you'll encounter it in like pre-calculus or like a little bit in calculus. It's like I don't know. I have very mixed feelings about trigonometry because like I think oh yeah, I guess you guys do it in eighth grade. Yeah. Okay, I don't know. Maybe this is something we'll do like in another time. But today let's talk about circles. Let's talk about circles. Not even the basics today, unfortunately. But maybe in the future we will try. Okay, cool, cool, cool. So I know a lot of you guys have been asking about an example. So let's go ahead and do one super quick. I will kind of, I don't know. I'm like conflicted. Do you guys want me to leave this up or do you guys think you like got it? Got it. Okay, cool. So I'm gonna like I'm gonna make it a little smaller and like put it to the side and then it'll really help you with this next problem. So, okay. So here is our next problem. Basically what we're kind of doing here is like match each of these like segments with these descriptions. So go ahead, put in the chat like what is A? Is it a tangent, diameter, chord, radius, and then do that for the rest as well. Mom asks, is there a formula for everything you said? So everything I said is actually a definition. There are no formulas involved. So it's important that you understand like what each of these terms means, and that's what we're practicing here. Okay, I'm starting to see some answers. Ah, it's already in order. Sweet. Okay, that's like a really nice coincidence. Cool, cool, cool. Oh, you know what? Hold on. Haha, I have figured out. I have figured out what to do. Okay, here's what we're gonna do. Okay, perfect. Yes, we could do a harder one. Okay, so let's talk super quick. AH is going to be the tangent because it intersects the circle at one point exactly. That's at point B. EI is going to be the diameter because as you can see, the segment connecting E and I passes through the center C. So that's going to be a diameter. DF is going to be the chord because it just connects 2 points on the circle. It doesn't go like past the circle. It starts and ends on the circle. And then CE is going to be a radius because it starts from the center and goes to any point on the circle. So yeah. Ashraf as isn't BC also radius? And that's correct because it's has 1 point at the center. Yeah, that's absolutely correct. Okay, fire. Yeah, I guess that was kind of easy because you guys already definitely saw the answers there. No worries though. So I'll make that smaller. Um, let's see. Hmm. Okay, I feel like you guys have got these down, like the parts inside a circle. Um, So let's go ahead and maybe talk about some relationships like between. Oh, I do see a question from Ashrid. Yeah, go ahead.
So my question was in the previous one when it said that I don't think they were asking for each one what it was. I think they're asking for the size that they didn't mention. What is it called? Like maybe they're asking for BC, GH, and like those two because there would be another reason why they give that order.
Um, I think it was just like accidentally in this order. But like if we want okay, you know what? Let's just go ahead and like identify some of these other ones just for like extra practice. Okay, so I do see a lot of people already saying like BC is definitely a radius. Is there like another radius that you guys see in this picture? I think someone said there were three. We talked about two. Is there maybe a third one? Yeah, so IC is also a radius because notice it's another point that starts at the on the circle and kind of goes to the center. Okay, stellar. And then what about GH? Is this what is this going to be? Yeah, GH is going to be a secant. And that's because it intersects the circle, but it also is a line that goes past the circle. The line part might be a little hard to see because there's not like arrows or anything. But because it like extends beyond the circle, we can kind of assume that it's a line. Okay, I think that's all the points on here. Okay, cool. Yeah, yeah, yeah. So this is like kind of easy. But that's okay because you guys already seem to like understand all the points on the circle. So let's now go ahead and talk about relationships between circles. So, um, oops, sorry. Okay, so we talked about tangent lines. We also have things called tangent circles. So tangent circles are basically circles that intersect at one point. So here's kind of an example. Um, Here we go. Okay, these are going to be tangent circles because as you can see, they meet at exactly one point right here. So that's why they're tangent, even though it's not a line, because they meet at exactly one point, we'll consider them tangent circles. Yeah, I think it like kind of, okay, the diagram precision is a little off, but the point is like these are tangents. They meet at one point. That's what I'm trying to convey. Okay. Um, Okay, cool, cool, cool. So like just a couple more definitions and then we'll kind of do some questions. So this is tangent circles. And then we also have something called concentric circles. Does anyone know what like concentric circles are? What are concentric circles? Any ideas? Ooh, and because they're kind of like inside each other. Okay, I think I'm gonna agree with that. So they have, oh, I like what Oshrid says. They have the same center. Absolutely. Okay, that's a really good definition. Okay, here we go. I'm gonna draw concentric circles. I can do this. Oh, darn it. Okay. Okay, so concentric circles kind of look like a radius almost. Uh, okay, perfect. So this is, oh my goodness, that was close. Okay, these also like low-key don't look like circles, but that's okay. So this is what we'll call concentric circles because they have the same radius. And I'll label this in blue, I guess, concentric. Okay, or sorry, they have the same center. Awesome. Okay, cool. Yeah, it looks very ellipsy, but that's okay. Okay. Cool, cool, cool. And then let's go back kind of to these tangent ideas and we'll talk about two circles again. So let's say I have like two, ugh, darn it. Okay. I think I'm gonna freehand circles. I feel like I could freehand circles better. Let's make these smaller so we have some more space. Okay. So I can also do, it was close. Oopsies. Nope, I'm not gonna try to freehand at all. Okay. And okay, so we have these two circles. Um, Okay. Guys, I do see a lot of like distracting comments in the chat. I think it's also starting to like distract me a little bit because I'm trying to like look for questions and stuff, and I just see a lot of like spam. So let's go ahead, cut that out because I think this might be new for some people, and I want to get through these definitions so we can get to some problems. So let's make sure we're staying focused, and if you have questions, like feel free to ask. But otherwise, let's go ahead and like keep the chat for important stuff only. Okay, anyways, back to the point. So we kind of have these two circles. And we're going to talk about a couple of tangent stuff here. So, let's say we have, see, we can kind of like draw a very particular line that is tangent to both of these circles. And so this line that kind of meets both of the circles at exactly one point is something we'll call an internal tangent. The reason why it's internal is because it kind of like comes inside the space between those two circles. So like this space here, that's like what we'll consider inside. So this is like an internal tangent. It's very like I think it's a very like weird idea, the fact that there's like an inside and outside in all this space, but we'll say it's like inside, because it kind of like comes between these two circles. Okay. If we also consider a different kind of, we'll consider two other circles. So we'll say, oops. Okay. So here's one circle, and we'll have a, oh gosh. Okay, and here's our second circle. Okay, so we have these two circles. So mom then asked, why isn't it called an external tangent? And that's a great question. It's not called an external tangent because this, hold on, that was so anticlimactic. Okay, there we go. Hold on, that was so anticlimactic. Oh my gosh, that was like, darn it. Okay, that was like the perfect moment. Okay, but my imperfect drawing skills have ruined it, unfortunately. Okay, here we go. Okay, so this is not called an external tangent because this is what we call an external tangent. This green line is external tangent. Okay, and let's see if we can move this so we have a little bit more space. Okay, I guess we, okay, perfect. Whew. All right, this is what we call an external tangent, and the reason why this is an external tangent is because, as you can see, it's kind of like on the outer part of the circle. So it's not in this interspace over here. It's on this outside bit, like kind of outside. So it seems like, how can you tell the difference between an internal and external tangent? Typically, an internal tangent will kind of be going like diagonally across the circles, and it'll kind of like intersect on opposite sides. But the external tangent will be kind of intersecting on the same sides. Yeah, so Malden asks, the internal tangent is between the two circles. Yes, that's a perfect way of explaining it. Okay, cool, cool, cool. Hithard says the tangent is outside of both the circles, but not in between, right? That would be for external tangent. Yeah, so it wouldn't be in between the circles. It would kind of be like on the outside. Yeah. Hall says, if it's called an internal tangent, why is it not inside? Good question, because tangents cannot be inside. If it was inside, it would intersect the circle in two places. So the internal part signifies that it's like in between the two circles. And tangents, remember, can only intersect in one place. So in this case, we're talking about the relationship between two circles and a line that is tangent to both of them. So that's why it's like an internal tangent. But you can never have a tangent inside an actual circle. Okay, cool. Okay, cool, cool, cool. Okay, let's go ahead and do a couple of practice problems. This time I will not give away the answer. Um, it's important to know like which one is internal and which one is external, because sometimes you'll have to draw your own diagrams. And they'll just say like, oh, here's an internal tangent. And then you kind of have to remember like what is an internal tangent. Okay, so here's our first question. Do you guys think these are internal or external tangents? Go ahead and put it in the chat. Okay. Wow. Okay. This is super fast. I already see lots of answers. Um, okay. a lot of you guys are saying internal tangents, and I would absolutely agree with that. The reason being, both of these kind of go in between the space of the two circles. As you can see, like this first one goes in between this space, and the second one also goes in between there. So both of them would actually be internal tangents. Okay, really good work. Um, we'll do another quick one. I'm sure you guys can like already guess the answer, but that's okay. Would this be internal or external tangents? Yeah, external. And that's kind of because they're like on the outside part. Otherwise, if they were internal, they would come somewhere in this space. But because they don't do that, they're gonna be external tangents. Okay, cool. So just quick, easy identification problems. We can go ahead and like move on to some more like complex stuff. Cool. There's not like a lot of difficult stuff about identifying like tangents and things. The harder stuff kind of comes from like I guess like drawing the diagrams with the circles and figuring out the properties and stuff. But once we get through the definitions, we'll get to some of those harder questions. Okay. All right, so here's our first theorem. Here is our first theorem. Wait, let me double check the chat, see if there's any questions. Mother asked if you make perpendicular line the way the arrow goes, show kind of wedged. Okay, yeah, that's true. Okay, good point, Marvin. I think that's a nice way of identifying. Okay, so I'm gonna make all of this smaller because we're gonna have a lot of theorems. Circles have so many theorems. It's definitely a lot. Okay, so here's our first one, which is the perpendicular tangent theorem. So what this theorem says is if there is a line that is tangent to the circle, then it is perpendicular to the radius drawn to the point of tangency. I'm not gonna write that entire definition because I think that's a little much. Um, but I will show you guys a diagram. Okay, let's do a diagram. Okay, so as you can see, we have a circle with center Q. We also have this like line. Oh, it got kind of like cut off. Here, I'll fix it. Okay, here's our line. And obviously like this line is tangent, right? Because it meets the circle at only one point, and that's point P. So what this theorem is saying is if you draw a segment from point P to point Q, first of all, this is a radius. And the reason we know it's a radius is because we're starting from the center and we're going to a point on the circle. But the point is, if you draw the radius and the tangent, you're going to get a right angle right here. So these two segments, or this line and this segment, is going to be perpendicular. Okay. Let's see. Questions, thoughts? Is this new? Is this stuff that you guys are like pros at? What do we think? Okay, Nahal says tangent, it's perpendicular. Yeah, perpendicular is a hard word to spell. Okay, cool. This is easy stuff. All right, let's go ahead and move on then. Um, that's like I think that's kind of like the main thing for tangents. Let's kind of talk about like angles. I think angles is a good place to be now. Yeah. Okay, we'll do it. Okay, today's class is definitely going to be a lot of different things, so we'll cover a wide variety of topics. So like, don't worry if we're kind of like jumping around everywhere. That's intentional. Okay, I'm just gonna like ask you guys these definitions because I feel like most of you guys are like pretty good about this. Yeah, that's what we just talked about. Yeah. Okay, so can you guys define like what is a central angle? What is a central angle? Ah, let's go beyond center angle. That's just like kind of saying what the word is back to me. What is a central angle? Or if you want, like, kind of like describe what it looks like. Okay, and Minnie says it's like an arc. I think you're like kind of getting to it, but like it's not necessarily correct. Okay, I like where Mika's going with this. It's something where you kind of have an angle starting from the center of the circle. And then Ashut says it's an angle formed by two radiuses at the center. Okay, perfect. I like that. Malden says a right angle arc. So I wouldn't agree with that because a central angle doesn't necessarily have to be a right angle. It can be like any angle size. Hittard says central angle is the angle between one radius and another. Okay, cool. So we have our circle, which is not going to be very good. We have our center, and then we have, oh, okay, wait, that was like kind of bad. Okay, so this is our central angle because it starts at the center. Okay. Yeah, this is like an oval. Sorry guys, my circle is set. Okay, so someone mentioned an arc. Let's briefly touch upon what that is. So an arc is like gonna be like a part of the outside of the circle. So like kind of the rim of the circle. Um, like here's our circle. So an arc is going to be like somewhere along this outside bit. We'll say a minor arc is something that is less than 180 degrees. So like this green stuff, this is going to be a minor arc. And then a major arc is something that is greater than 180 degrees. Gosh, I don't want to do Christmas colors. So this is going to be a major arc. Okay. Um, Cool. And then a semicircle is basically like an arc whose endpoints are the endpoints of the diameter of a circle. So like a semicircle is just half of a circle. Yay, that's a bad semicircle, but I think you guys know what a semicircle is. Okay. Um, okay, so basically like when you're naming an arc, we assume that it's always a minor arc. So if I had named these points like uh let's see, like A and B, if I'm referring to like A, B, and then like this arc symbol, this is minor arc AB. Okay. But if I had talked about like major arcs, I would need a third point to talk about it. So like there would have to be some third point on this side, like C, and then I would have to say like ACB is major arc. And that's kind of how I know that it's going the other way. But yeah, so like that's kind of the big thing with arcs. Someone asked like what happens if it's exactly 180 degrees? That's what a semicircle. And semicircles are always described with 3 points as well. Okay, cool. Um, cool. Let's see. I'm just kind of thinking like what's good to cover next. Uh, we'll skip all of that. Okay, here's a good theorem. Okay, cool, cool, cool. We have found a good theorem to talk about. Amazing. So I'm gonna close all of this. This is all definitions. Seems like you guys are familiar with this. Our next thing, no, it is actually not circumference. It is about chords. So it's kind of like about chords, but also like arcs. Okay, so basically, if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. Okay, that sounds crazy. Let's put it in a diagram. Here we go. This is our diagram. Basically, what I'm saying is if we have the diameter of this circle, obviously this is going to be this thing, even though we don't know like where this point is, because it's something that goes through the center, we can say like this is the diameter. So we have this diameter, and we know there's a chord FD. So because FD passes through the diameter, like it intersects the diameter, we can say that first of all, these two segments, these two chords, are going to be perpendicular. Okay, but the second thing we can say, and this is actually a lot cooler, is that the diameter actually bisects the chord, meaning it splits the chord into two equal parts. And not only that, it also splits this arc FD into two equal parts. So we can say like these two are equal and these two lengths are also equal. It's like this is really cool. Okay, is this something like that is maybe a little newer or like something you guys have also seen before? Just like curious. Because if we need to spend like more time or do a problem on it, like we totally can. Okay, cool, cool, cool. This is cool stuff. Okay, great. So we'll go ahead and move on. I just think this is like pretty neat. This is definitely pretty important. These theorems definitely can solve problems or like be a big factor in solving problems. So this is stuff I would like definitely remember. Um, this is gonna be one of those few times that I kind of just like introduce the theorem and don't go into the proof because if we kind of go into the proof, it'll take up like more than an hour. It'll take up a lot of time. So we'll kind of just like talk about the different theorems and then we'll learn how to apply them in problems. So. Cool. Okay. Da, 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 da. Let's find another good theorem. Okay. Actually, I feel like this is a good point to do some problems just because we've talked about a lot of different things. So no more theorems. Let's switch to problems. Okay. Just like again to say, like I know we're doing like a lot, a lot of like random things today. Like we're just talking about so many random problems. So if you're feeling like confused or like overwhelmed or like you're just like, okay, what is happening? Um, Please ask. Please ask. Okay, here is a circle that we have. It is going to be kind of an odd looking diagram. Uh, See if like maybe I can crop it a bit. Okay, I have no idea what I'm doing. That's fine. It's not a big deal. Okay. Can you guys tell me, is EC like tangent to hmm. Is EC tangent to the circle? That's my question. Is EC tangent to the circle? What do you guys think? Okay. Yay, that's so much better. Okay, is EC tangent to the circle? Yes, yes, kind of, yes, definitely, yes, sure, yes, uh-huh. Because says it intersects a radius. Okay, very interesting. Cool, cool, cool. Now, do you guys remember one of the first lessons we talked about in geometry? Can you trust the diagram? Can you trust the diagram? No, you cannot trust the diagram. So, even though it looks like EC intersects ED at a right angle, can we say for sure like this diagram accurately represents the relationship? Like, is this true? Okay. I see some of you guys are, oh no, what the heck? Okay. Okay, I see some of you guys are saying yes. But Manit says no. Okay, cool. So what are we gonna do? Manit says use the Pythagorean theorem. Okay, this is something I like because remember, if we like assume this is a right angle, then this should be a right triangle, right? Like this should be a right triangle that we can check. So let's go ahead and do exactly that, okay? So what we want to show is like, is 11 squared plus 43 squared equal to 45 squared? Okay, so there's a couple ways you can go about this. Like maybe you want to do the calculations, and if you want to do that, like great. Another way you can do this is like kind of looking at like the last digits and being smart. Um, so if we look at the last digits, what number does 11 squared have to end in? Like what digit does it have to end in? Amiga says it intersects the radius, so it is 100% tangent. It looks like it intersects the radius, but once again, like we can't trust the diagram, right? So we don't know if this like is actually like intersecting the radius or if it's just drawn to look like that. So that's like you can never ever trust the diagram. Like everything you do in geometry has to be like proved and like verifiable. Um, okay. Yeah, so I see a lot of you guys already calculating 11 squared, and yeah, that's like 121, so it ends in the digit 1. What does 43 squared end in? Maybe you want to calculate this. I personally don't. Okay, but I see a lot of you guys saying it ends in 9. And that's pretty easy to check because this last digit is 9. So if we square it, obviously this ends in a 9. And what does 45 squared end in? Yeah, it ends in a 5. For the same reasoning, the last digit is 5. If we square that, you get 25, so that last digit is 5. Okay, so as you can see, we have a 1 and a 9. We have a 5. So obviously, like this doesn't match up. The unit digit don't match up. So this is not a true equation. And because this is not true, like Pythagorean theorem is not satisfied. And because Pythagorean theorem is not satisfied, this cannot be a right triangle. And if it can't be a right triangle, there is no way that this is the radius and this is the tangent. Obviously this is the radius, so this cannot be a tangent. Otherwise, it would be a right angle. But we just showed it can't be a right angle because it's not a right triangle. Okay, so this is kind of like a really important lesson. The calculation part is not the important part. It reiterates this big thing in geometry, and you guys really haven't seen this up until now. But this is really showing like you cannot trust diagrams in geometry. It doesn't matter whether it's given to you or whether you draw it. Anytime you do something in geometry, like you have to show that this is like correct. You cannot like trust your eyes. Like something's gonna go wrong. Like diagrams are not to scale, diagrams are misleading. Everything you do has to be like proven. So like take caution, like be cautious. But yeah, this is like a really good example of that. Cool. Cool. So that's like I think that was a good like tricky example. Yeah, if you guys have questions on this, please ask. Otherwise I'll keep kind of like going forward. Okay, no questions. We'll give like more problems in the homework. So if you guys want more problems on this kind of stuff, like yes, you will get it. But I just want to cover a couple more theorems before we end today. So I'm gonna go ahead and like minimize this. Okay, our next theorem is going to be, again, about tangents. Like I said, tangents are super cool, super relevant. So here's basically our next theorem is like saying that if we have two different lines and they start from the same like exterior point and they're both tangent to the circle, then these two lines have the same length. So let me go ahead, put another diagram to show you guys what I'm talking about. Okay, so here's our diagram. In this case, as you can see, we have two different lines. They both start from S, and they both are tangent to circle P at these 2 points. So what we'll say is that these two segments are equal. So RS is equal to ST. Okay? Yeah, I would say like these are it's one circle, so you can't really say if it's external or internal. Yeah. Can't really say much. Because if the circle is like on this side, it would be external. But if the circle was on this side, it would be internal. And actually, there are like problems based on this kind of thing. There are problems that like look something like this diagram. So yeah, that's definitely something that like crops up for sure. Okay, anyways, that's kind of the point here. Yeah. Okay, let's do a quick problem with that. Mm-mm-mm. Okay, so here's our problem. I want you guys to find the value of x. What is x? Ah, super fast mini. Let's see if anyone agrees. Okay, 3. I think that's pretty simple because like we just said, these two are going to be equal. So 11 is equal to x squared plus 2. X squared is equal to 9. So he's taking the square root. X is obviously equal to 3. Okay, good work. Cool. Alrighty. I think at this point we're kind of just gonna do a bunch of problems. I don't know if there's any good theorems to talk about in such short time. Maybe like one more small one. But anyways, okay, let's go back to like maybe finding some angles. This time I will not give you any answers. Okay. All right, so go ahead, find the measures of arc LM, arc MNL, and arc LMN. Okay, so I see a lot of you guys saying that LM is obviously 70, and I absolutely agree. Because remember, with central arcs, or with central angles, like whatever arc they like subtend or whatever arc they kind of like span, it's gonna be the same exact length. So in this case, like because this like central angle is 70, our arc length is also gonna be 70 degrees. Okay. All right. Does anyone have any answers for what the arc M and L will be? So M and L is gonna go this way. I'll like outline it in dark blue, I suppose. So it'll kind of go like this. So what is M L. What is that length? Yeah, 290. Okay, perfect. That's just 360 minus 70, right? So 290. And what about LMN? Okay, I see a lot of people saying 180. That's absolutely correct. Because remember, LN is going to be a diameter. So in this case, it'll be 180, half the circle. Okay, amazing. We'll do a couple more angle questions. Okay. I don't want to do that one. Okay, we'll do this one instead. But first, I gotta clear up my screen. So much stuff going on. Okay, so here's our next question. Find the measures of the red arcs, and then let me know. Do you guys think these red arcs are congruent? This is kind of a interesting question, I'd say. Okay. Um, I see a lot of you guys saying that these are congruent. Okay, awesome. So let's take a look, right? Obviously, like because this is a central angle, like we can say that the measure of arc DE is going to be 81 degrees, and the measure of arc AC is also going to be 81 degrees. So you would think these are congruent, right? But again, this is another trick question. Because remember what congruency means. It means they're the exact same in size and shape and length. But we can clearly see like these are not the same in length because their radius, they have different radii. They have different radiuses. For example, like this is a smaller circle than this one around it. And so obviously like because they have different lengths, their arcs are also going to be different, even though they have the same measures. So this is something really, really important. You can have the same angle measures, but have completely different arc lengths. And that's because arc length depends on your radius. So that's why these arcs are not congruent, but they are gonna be the same like measure. Okay? Does that kind of make sense? Like, is that clear, like why these are not congruent? Because this is pretty important. Um, a pretty important property. Okay, cool. I think I'll end with one more question, and then we'll kind of leave it for next week, where next week we'll talk about more like complex definitions and then get into some of like the really neat circle problems. Okay. But anyways, for tonight, here is our last question. So find the measure of angle BC, or I guess arc BC. Okay, and Vika says 37. Okay, cool. Let's take a look. Okay, so because we know Okay, so we have kind of like two different like triangles here. So this might seem kind of weird, like, because why am I talking about triangles, right? But we'll explain, right? So we have two different triangles. Obviously, like we know AD and BA and AC, these are all going to be the same length. And that's because these are all like radiuses. We also know like BD is BC, that's given to us because like that information is given to us because like they're marked by the same symbol. So we can tell like BAD and BAC are obviously like congruent triangles. These triangles are the exact same. So that means like these angle measures are the same. And remember, like these angle measures are relating to the arc BD and BC. So because these are the same, we can say BD um, and BC have the same angle measure. And we know that that's 3x and 2x plus 48. We're already given expressions for those. So if we go ahead and like kind of put that into the equation, like substitute those here, we get 3x plus 11 is equal to 2x plus 48. So if we go ahead and solve for x, we'll find negative 2x, negative 2x. We get x plus 11 is equal to 48. So x is obviously 37. But remember, we're trying to find the measure of angle BC. So BC is 2 times x plus 48. So that would be 2 times 37 plus 48, which is equal to, let's see, 74 plus 48, which is 122. And that is our final answer. Okay, and we'll go ahead and end class right here. If you found today a little bit easier or kind of like a little bit of review, that's totally okay. In our next class, we'll kind of do some more complex definitions and some more complex problems. So I hope you guys will join me then. It'll totally be exciting. Otherwise, thank you all so much. I hope you learned something new, and I will see you all next week. Bye, everyone. Thank you so much. Have a great week. Bye. Bye, Amari. Bye, Rashab. Bye, Jason. Bye, Monbeth. Bye, Hidarth. Bye, Kevin. Bye, Oshrid. Okay. I don't see any remaining questions, so I'm gonna go ahead and end the Zoom, but always feel free to email or reach out if you have any questions whatsoever. Bye, everyone.